So hello everyone, welcome back to my channel. In the last video we have done the URDF tutorial in which we have learned how to make the URDF file for a 6 degree of freedom robot. Continuing with that series, in this one we will explore the kinematics of the robot. So kinematics is basically dealing with the velocities of robot, just ignoring the forces and dynamics of it. Broadly classifying the kinematics, there are two types of kinematics, that is forward kinematics and inverse kinematics. So in this video we will go through these forward kinematics. I will explain you what forward kinematics is. We will show the demonstration on the simulated robot on Harvey's. We will understand the mathematics behind it. We will see how to make it working the forward kinematics of any robot. So first let me go through a demonstration of forward kinematics. So here I will launch my node for Harvey's as we have done in the previous video. Now I will run my forward kinematics node. So this is my forward kinematics node. So what forward kinematics is basically is we are given with the joint angles and we will find the end-effector position. End-effector position means position of this point. So I am publishing the end-effector position on this topic, that is this one. So now what we are going to do is, as I will change the joint angles, you can see that the end effector position and orientation will change. As you can see here, it is changing. As soon as I change the joint angles, the end effector position will change. You can clearly see as I do the center. So it will. So now you can see that this red one is the x-axis, green one is the y-axis, and blue one is the z-axis. So you can see that in this position, this is the end effector and it is in xz plane because this is y-axis. So y is 0, you can see here y is 0. So therefore we can see that our end effector position is correct, means forward kinematics is correct. If we do some randomized angles, so these first three are the end effector position, second three are the end effector angles, that is roll pitch yaw angles. So this is what forward kinematics. This is basically the demonstration of forward kinematics. So now I will explain you what is forward kinematics. So it is basically computing the position and orientation of robot's end effector given the base joint angles. So how is it done? So there are some steps you have to follow to do this. First of all, you have to define some reference frame for your robot. Then second step is finding the transformation between those frames. Then we will multiply all these transformations and at the end we will get a transformation matrix from base frame to end effector frame. So you can come here. So this I have made for my robot, what I have demonstrated in my video. So this is my base frame, this is my end effector frame. I will find the transformation matrix for each frame. I will multiply all the transformation matrix and I will get a HTM, homogeneous transformation matrix, that will map from this base coordinate to end effector coordinate system. That is in DH frames. So the last column, the three entries of the last column will depict the XYZ. For example, this is a HTM matrix, so these three will depict the end effector position at the end when I will multiply all of these. So how it starts? So on the left hand side you will see these are the actual joints of my robot, and on the right hand side you will see these are the DH frames I have assigned to it. How I have assigned these DH frames is I have followed the basic procedure that is required to assign this DH frame. So I will also attach a manual with this video. You can just read through it, and these are actually like some rules you have to follow to assign, but you have to make sure that these all lengths get into our DH parameters. So I will show you what DH parameters in some time. So these all lengths must be taken care of while writing the DH parameters. So after assigning these reference frames, the second is to find the DH parameters. So these are the DH parameters. So basically these are 4 parameters for any joint or any link. So these two are link parameters, these two are joint parameters. So we'll define it for all the joints. So after finding these, so how we find this, that is also in that manual. So basically these are the angle between z-axis, distance between the z-axis, distance between the x-axis, distance between angle between the x-axis. So this is the procedure, and once these DH parameters are done, then you have to find the transformation matrices. How to find the transformation matrix? So we came through a formula that is zyx or zyz something. There are various Euler angle transformations for this. So for example, if you are using zyz, if you are using zyx, anything we can use. So we will get this transformation matrix, and this is very important. For each frame transformation we have to define this transformation matrix. Once this transformation matrix is defined for each frame, for basically parameterization, for mapping between each frames, then we can multiply all those transformation matrix and get a map from base frame to end effector frame. So first thing, reference frames we have defined. Then we will define the homogeneous transformation matrix. After defining the homogeneous transformation matrix, we will multiply all those transformation matrix to get my end effector homogeneous transformation matrix, that is final matrix. So once I get this final matrix, then I can easily get my end effector position. So you might not able to visualize what I am saying through these all formulas and all. You might be a bit confused, but don't worry, I will go through the code. Once I will go through the code, then you will understand everything that what I am saying. So I will also take reference from the documentation, as well as I will show you the code. So as I tell you that first we have to define those DH parameters. So I have defined the DH parameters. I have used this theta. Why I have used this adjusted theta? As you can see in my DH parameters, what I have done this theta 1 plus pi by 2, theta 2 minus pi by 2. So these theta 1, theta 2, theta 3, theta 4, theta 5, theta 6 are the joint angles which are given by user. These are the inputs. As I have told you, joint angles are given as input, end effector position is the output. So adjusted theta is given as input. As you can see, it for this function calculate fk, this is coming as input. Then we are adjusting it according to our need. Then what we are doing, this I will show you, I will explain you in some time why we are doing this. We are starting a for loop. We are just finding that matrix from where this matrix is coming. So you can see this is this matrix only. So what we are doing, we are just multiplying it for the number of joints times, and multiplied number at the end, like nth time when this loop is executing, so we will get a t temp. So that will be our homogeneous transformation matrix. And how to get the end effector position and end effector rotation from this matrix is I have written in executable file. So I have written the logic file and executable file separately. So in the executable file I have defined my all the ROS nodes. So basically it is inheriting from this ROS node. Then you can come directly here, like calculate fk. So what I got here is a eigen matrix T. How I am taking the position from there is basically taking the 3 elements of the last column, and then I will take the rotation matrix and I will convert the rotation matrix to Euler angles. Now I have defined this function. So this is the basic mathematics to find the Euler angles from the rotation matrix. That I will also try to share the documentation of how this is done. But this is, I think, very basic. That is just applying tan inverse formula, nothing more than that. Now coming to the logic. So I told you that why I have used this. So if I go to my DH frames, you will see that my sixth frame is at this point, but end effector is this point. Now why I have taken my sixth joint here? As you know that for a 6 degree of freedom robot, to solve the inverse kinematics analytically, means algebraically, if we want to solve that, we want that 3 axes are intersecting at a point, and DH frames we take here, so that the position of this point will only affected by joint 1, 2 and 3, and it will not be affected by joint 4, 5 and 6. You can see that as we rotate joint 4, joint 5 or joint 6, the position of this point will remain same. So you can easily see that. So to go from this to this, I have done this part. So you can see that I have also added this L7 LE to my positions, because you can see that this is L7 and this is LE. So I have added that, and for my theta I have added minus pi, because I have taken the frame in that sense. So I have added here minus pi. So in this way this whole logic is working, so that I will get the position of this point. So I think you got the idea of how this forward kinematics is working. So in the upcoming videos I am also going to explain you the inverse kinematics that I have already done, and then we will go to joint space planning, then we will go to Cartesian space planning. We will do all of these things in the upcoming videos. So thank you for watching the video. If you like the video, then subscribe to my channel and also like the video for support. Thank you.